All right, so in this kind of final set of slides for the term, I just want to give you guys some general tips for state space tracking. I think I've got 5 of them. And then I've got two examples included here where I go into some depth of applying these techniques to some so real data. Both examples use real data. So this is a little bit like the project presentations you'll be giving in a week. This is just 2 examples right now. Well, same the term, just 2 examples. So you've heard me say this before, and I'll show you a really nice example of how it's been helpful to us in some of our work, but innovations are just key when you're working with real data. We're often working with additive noise. Standing assumption is that they're white, although, as I've mentioned, and as you'll find in the book, there are ways of generalizing so that in relaxing that requirement that the noise is white. And if our estimates are perfect, if everything is going well, then the residuals will be a white noise sequence. It's true for the state error, as well as what I've been calling the innovations, the difference between yn and our predicted value of the measurements. You can calculate from all the different state space trackers that we've been working with. So even if the estimates aren't perfect, and I hope you've got a better understanding now of what we mean by perfect. Of course, we want to estimate the true state as well as possible, but really you should be thinking about the optimal marginal posterior, what the true mean is of the posterior. That's really what we want to get as close to estimating as possible. The true state may deviate just due to random chance, but that we're trying to get to that. And again, the residuals should be white noise. For those of you that took that class with me a year ago, you've got lots of ways for figuring out whether a sequence of measurements is white noise or not. You can look at it in the frequency domain, look at it in the time domain, look at it in the so-called lag domain by looking at the autocorrelation. There are lots of different techniques you can use to determine whether it's white, and if it's not white, to understand how it's not white. And again, you'll see a really nice example today. And with real data, you can always look at the innovations. So use innovations. They're the key tool for tuning and diagnosing and making sure that things are going as well as they can. And I don't think I have this as one of the tips, so I'm going to add another tip. I'm going to have to do this kind of on the fly. Tip 6. It's going to be out of order. I think there's only 5 tips. Track with synthetic data. Synthetic. So I guess there's kind of 3 different components here. Create synthetic data. If you've got your state space model, you ought to be able to synthesize data. The only time when that really becomes tricky is when you've got very strange noise driving your process model or your measurement model that may be hard to model if it's not Gaussian, for example, but something complicated. Some of you had some examples like that. The other case where that can be difficult is when your model has external inputs, when you've got external measurements that are driving your model. But if you've got recorded data, then you can still fold real recorded measurements into your model and still create synthetic data that way. And it's often instructive to compare your synthetic data to the real data. We're just looking at it and characterizing it in the usual ways. Do they have similar power spectral densities? Do they have similar limits if your process is stationary? Are they bounded in the same way? And that can give you a lot of clues as to whether your model is accurate or not by comparing properties of the synthetic data to the real data that you're working with. And of course, apply the data, as we've been practicing throughout the term, apply the tracker to synthetic data as well and make sure that it at least tracks well with the synthetic data. It should, but if it doesn't, that may give you an idea that you need more particles, for example, if you're working with a particle filter. So you can do sweeps and you can do tuning on the synthetic data where you know what the true state is and you can get really good performance measures and then apply it to real data. So that's just good engineering practice to work with both synthetic data and real data. With the nonlinear estimates, when all of you should know by now that when you've got a nonlinear function of a random vector, that the expected value of y is not just taking your best estimate of the state and pushing it through that nonlinear function. We saw an example of that I hope was compelling, where we say x is a normally distributed random variable with some mean and standard deviation, and we just simply, our nonlinear function is a square. If you take the mean and put it in the nonlinear function, you get 0 as your best estimate of what this is. But we know the expected value of a squared normally distributed random variable is actually the variance. So we went over that when we were talking about the Kalman filter. And it's just a nice example to keep in mind to make it very clear that in general this is not true. So with particle filters, you've got these random samples. You've got all your particles. And what you should do is push your particles through that nonlinear function to create your outputs, and then take the same weighted average of your outputs as your particles to get your estimate of what the measurement is. So that's the technique that you use. If you've got, and that works with other nonlinear functions too. Sometimes you're not as interested in the state of whatever the state vector is. It may be that you're interested in some nonlinear function of that state rather than the state itself. And if that's true, then you shouldn't just take your best estimate of the state, the weighted average of the particles, for example, if you're doing the mean, but rather feed each of those particles through the nonlinear function and then take the weighted average of that. So it's true whether you're talking about the measurement model or if you're talking about some other nonlinear function of the state that you're trying to estimate. So for example, your state vector may have the velocity in units of how the heading angle is changing and how the velocity of the thing that's moving is changing. So if you're tracking objects in water, where that kind of model may be more accurate, because the dynamics may be that it can't turn very fast, but it can accelerate and decelerate very quickly, for example. But maybe you're interested in the translational velocity, so that would be a nonlinear function of those elements of the state vector. So if you're working with particle filters, this is what you'd want to use basically to calculate that. Think really carefully about your prior knowledge. A lot of engineers, even experienced engineers, will not be careful about the process model, or say, oh, I know how to drive a Kalman filter and send a Kalman filter. I'm just going to make up a process model, feed it a lot of noise, and go. And they're really losing out on an opportunity when they do that, because if you don't have if you're not encapsulating the prior knowledge you have well in the process model, then you may as well be doing just straight up estimation techniques, such as minimizing mean squared error or maximum likelihood. There's a whole body of estimation techniques that you can use that's outside the Bayesian context if all you want to listen to is your data. That would arguably be true with adaptive filters, with least squares estimation, with a lot of the things that you learned in 539 for those of you that took that class. So this class was about state space tracking, and a key component of state space tracking is the prior knowledge that you're bringing to bear on your problem, whether it's knowing that it's within certain bounds, whether it's knowing that you've got a car going around a track and you get maybe more elegant, as Met did in his homework project, where we say, well, we've got the car and it's got momentum as well, and it can only speed up and slow down so quickly. There's usually a lot of prior knowledge you have, and that all goes in the process model. And so thinking really carefully about capturing the state dynamics as well as you can in your process model can really help you track a lot better. And we just saw an example of that with the unscented Kalman filter, where our prior knowledge of that thing's going around the track. Without that, if all we had was measurements, it'd be kind of hopeless whenever you got to one of those bifurcation points of knowing whether the car was going backwards or forwards. And we saw when we had kind of weak knowledge about whether it was going forwards or backwards, where there's a lot of noise and it's not moving very fast, so it's hard to tell what direction it's going. But then suddenly up the speed, and we were able to track far better with unscented Kalman filters. So that's a good example where better prior knowledge enabled us to track better. So don't be sloppy with your prior knowledge and say, I don't know, random walk, huge variance, and really relying on the likelihood. If you're going to do that, there are other techniques that you can learn about in another class or other books that are well suited if you really just want to listen to the data. But this is about combining what the data is telling you with the prior knowledge. So spend the time to think carefully about your state space model. Make it as accurate as you can. And I put up an equation here. I'm not even quite sure this is right. Iris, you've done this, so I'm hoping that you can tell me whether I got this right or not. But is an example of that, if we've got a boat or an airplane or a drone or something that let's say just for the moment is in 2 dimensions. I'll make it a boat. So the boat is going forward, and it can only turn at a certain rate. Sort of the lazy way to model this would be to say, okay, the position at time n plus 1 is equal to what it was plus the sampling interval times the velocity. And I know this is a simplistic version of doing the integration. There are better ways of doing it, but it's good enough if the sample rate is high enough. And then we say our velocity at time n plus 1 is equal to what the velocity was plus noise. So this is a random walk model for the velocity. And it's not very good because it suggests that this boat is just as likely to take its next step in this direction as it is in that direction. And I mean, that's not what boats do. And yeah, I mean, the velocity kind of builds, I guess, after a while if you were estimating it. But nonetheless, it says the change in velocity, and maybe this is another way of looking at it, the change in velocity where it's being driven by this noise is just as likely to go left, or I guess would that be starboard or port? One of those two, as it is forward or backwards. And it's just not capturing the dynamics very accurately. And with boats, it's usually far easier to make them accelerate suddenly than it is to make them decelerate. You don't usually have water brakes on these things, and so all you can do is kind of cut the motor and coast to a stop. And so there's nonlinearity in terms of its ability to accelerate or decelerate. And those are all dynamics that you should capture in your model if that's knowledge that you have for what you're tracking. I've mentioned a couple times that there's another model you can use, and I don't know if I got this right. I meant to look it up, but I just ran out of time. But you could, just as before, say the position in 2 dimensions, this is a two-dimensional vector, is equal to what it was plus the sampling interval. And then I've got the velocity, but now I'm expressing it in a different form, in polar coordinates, basically, where I say, well, you've got, try to draw this. If this is where the boat is at time n, then arguably it's got some velocity in the angle that it's moving in, and basically some bearing angle. And then we could separately say the bearing angle, and we could model the bearing angle as a random walk, and the change in the rate, I couldn't use velocity because I'd already used it, but basically it's forward velocity at time n plus 1 could also be modeled as a random walk. But now you can separately, by setting the noise for these two parameters, you can much more intuitively and have finer control over whether this thing can turn rapidly, whether it's a jet ski, or whether it's a tanker where turning takes a really long time by now dialing the noise on the rate at which it can turn. Is this similar to what you did? Mm-hmm. Yeah. Okay. So that's an example where you can better capture the dynamics if you put some engineering into the design of the process model to really capture what it is that the dynamics of whatever it is that you're tracking. Okay. And then I just wanted to mention briefly, we saw an example that was, in some respects, a little bit silly because you would never do it this way, but I did it anyway at the time to make some other points, where we had an accelerometer tracking something in 1 dimension without the effects of gravity that was moving really quickly. And I used a random walk model for the position, but physical objects don't move that way. Newton's laws don't usually quite work that way, where the position can change that erratically. Usually they're much smoother than that. And so this is a random walk model for the position, but you could just as well do a random walk model for the velocity instead, where you say the position at time n plus 1 is basically a first-order discrete time approximation of an integral of the velocity, and then you've got, and each of these could be vectors in however many dimensions you're tracking, 1, 2, or 3. And then we've got the velocity at time n plus 1 is equal to what the velocity was plus noise. So that would be a random walk model on velocity. More realistically, usually what the thing that can change suddenly is the acceleration. And so you could also take it one step further and have the acceleration be a state variable. And you can model the acceleration as a random walk. Or you can make any of these or all of these autoregressive processes as well, When you're tracking human motion, I know that the acceleration is not going to be sustained. I know that average acceleration for human movement is going to be 0 because over time we don't take off to the moon. And so it would be more reasonable in this case to model this maybe as a random walk process where there's an alpha there where alpha is less than 1 and greater than 0. So in that case, I'm now would be modeling this is an autoregressive, a first-order autoregressive process, which has 0 mean. So those are things you could do. But think carefully about your process model and what it is that you know about the physics of what you're tracking. I know for those of you with a controls background, you have a lot of practice at this, but for those of us that are much more on the signal processing side of things, you may have less experience really thinking about the design of the process model, and it's important. I mean, that gives you kind of half of the information that you get to work with. You've got the data and you've got your prior knowledge, and the process model is where you put most of your prior knowledge. Tip 4, work with real data. Real data always surprises you. You'll get it working beautifully in synthetic data, and it will never work out of the box, first go with real data. Real data always has warts, and the tracker is just never going to work well the first time. And I shouldn't say if it doesn't, I should say when it doesn't. I think, once again, I emphasized this before, but the innovations are probably your best tool in working with real data for figuring out why it's not working. They can show you aspects of the signals that you didn't capture in your model that you needed to. And this probably should be a different tip, but the rate at which the tracker is able to follow the state, kind of the trade-off between bias and variance, is usually in the magnitude of the process noise. The more process noise you have, you're kind of reducing your prior knowledge, and you're giving it a lot more flexibility to just listen to the data. So the bias-variance trade-off that we talked about near the beginning of the term is primarily controlled by the process noise variance, which is usually a knob that you as the engineer as part of your design process are turning. Yeah? And then, and I will get to some examples that are not just words. I promised you earlier that I would explain how to incorporate the fact that you're often working with sample data. And the answer is you usually leave your measurement model alone. But in general, and I hope all of you do this, I see kind of junior engineers will code something up and they'll hard code in the sample rate somehow, and then they'll design an algorithm, but the algorithm only works at that sample rate. And I hope all of you, if you're doing good signal processing design, it will work even if you change the sample rate by a bit. I mean, there's considerations with Nyquist and how good the numerical integration is, but if you're sampling something at 100 hertz, and someone suddenly gives you a signal at 120 hertz or 150 hertz, it really should work just as well. You just tell a different sample rate and it just goes. And so you should, as part of that good practice, wonder, well, how do I have to change my state space model? If you're working with additive noise, then the answer is that our process models often are often like a random walk. If you've got a random walk, then the uncertainty of the output of a random walk, the variance grows linearly with the amount of time that you wait. So if I had a random walk and they all started at 0, some will go negative, some will go positive, some will go up and then come back down. But on average, the variance of this group grows linearly with time. I probably should have scaled that so it grows a little bit differently, but the variance grows linearly with time. So the short answer, without going through the kind of math that we saw in one of Iris's presentations, is that you scale the standard deviation of your process noise by the square root of t, and that will usually make it so that it's invariant to changes in the sample rate. If you're taking if you're waiting a longer period of time with a random walk model, then that means that you've got, you're taking a bigger step, is what that's equivalent to. So that ends up being the short answer to that question. There's much more math behind that I'm sorry I didn't have time to go through this term. So, but the main point is, make sure that your design is invariant to changes in the sample rate. And that's true not just in this class, but in general, that should be true. And that brings me to the first of two examples. I think this is a good point to take a break. So let's take 5 minutes, and then I'll walk you through the two examples with real data points and again, real data. So I think most of you know I've got I founded a company a while ago that makes wearable inertial measurement units. These are all over the place now. We founded the company before iPhones existed. So it was a different world back then. But in any case, we've got these small IMUs that record data. And in this case, I was interested in tracking planar motion. You could think about using an IMU as a type of mouse that doesn't have any kind of optical interface or a trackball or anything like that. You could do it maybe just on the inertial measurement unit itself, just on the inertial data. And so in this case, the sensor data that I had to work with are the X and Y axis of the accelerometers and the Z axis gyroscope. So it's a two-dimensional object. I don't think I have a diagram in these slides, so I can sketch it out. You know, the IMU is roughly square-shaped. And the Z axis, we've got some rotational rate. And then we measure in the sensor frame what the acceleration is in the X direction and in the Y direction. So it looks something like that. And I have very limited knowledge about the movement, so you could wonder, well, why are you using a state space tracker? But some of the prior knowledge that I'm able to bring to bear is that both the accelerometers and the gyroscopes drift over time, and they drift slowly over time. So there's a bias to the sensors. The sensors aren't great. It's not just white Gaussian measurement noise, but there's an offset that you often encounter with these sensors. So you can't tell from this data, and this is part of what makes signal processing really fun for me, is when you've got a problem and you record the data and you look at it and there's no way you can make sense of it visually. You can turn off the light if you want. I'm sorry, the projector isn't very good. And I used too thin a trace, but basically what you see is that this is a recording that is 13 seconds in duration. And you can see that there's very little activity on any of the signals. The top plot is the x-axis of the accelerometer. The middle plot is the y-axis of the accelerometer, and the bottom plot is the z-axis of the gyroscope. So it's in units of radians per second. And you can see that the signal only exists for a brief period of time, and then it's quiet again. And when you look at that data and you think, okay, what on earth did he do? What was his movement? How did he generate this data? It's planar motion, so you can imagine there's an IMU on the desk, and I did something with it for a brief period of time. And you can see that whatever I did only lasted from about time 3 until about time 8.5. So it was only about 5 seconds in duration. But I moved it in some way for 5 seconds, and you can't tell by just looking at the data. Like, there's no way. Pardon?
There are loops they're making.
There's loops?
Yeah.
Well, we'll see. We'll see. Scott, you can turn the light back on if you would, please. What's a good guess? The sensors are calibrated, and I've got a good idea of what the noise power is on them. I mean, these sensors are well characterized. But theoretically, to get at some of the other prior knowledge I'm going to bring to bear and how I incorporate that into the design, with IMUs, you can't distinguish between something at a constant translational velocity and something that is perfectly still. But in most of the applications that I work on, we're tracking human movement, and humans never move with linear translational velocity because it can't. We've got joints, and it's really hard to move in a straight line, so it never happens naturally. Certainly didn't happen in the way that I was moving this thing on the table when I made this recording. So if there's movement, you're gonna have some power in your signals. It's not like it's just gonna be constant, even though it could theoretically. And the gyro, so if there's one of the assumptions is that there's never constant velocity, there's only ever periods of zero velocity. And so that was part of the prior knowledge that I'm bringing to this problem, is knowing that if none of the sensors are showing anything, then it's still. It's not that it's at constant velocity. I'm not driving down, I'm not on rails on a train making this recording. I'm stationary, at least relative to the Earth frame. So I made a simple detection algorithm to detect when this is at rest and when it's not. And basically, if the gyro signal power is less than some threshold, then I can assume that it's at rest and we've got zero velocity. Otherwise, I don't have zero velocity. And the algorithm design, I only use a gyroscope just to make it simple. I've done much more elegant things, but this was easy to do and easy to explain. And it's not really the emphasis anyway, so we shouldn't get too caught up in how well the zero velocity detection algorithm works. I haven't even shown you yet why I'm doing this. But it's easier to work with a gyroscope, and I don't have to worry about the confounding effects of gravity when I do this. I applied something called a kernel filter that's related to the kernel smoothing we did earlier. It's basically a low-pass filter that has a non-negative impulse response. So that means it never produces an output that can go negative as long as the signal coming in is not negative. So it's just a type of low-pass filter that I like to use in a lot of my applications. And I'm sorry this got cut off here. I don't remember what I was going to say there. But I used a cutoff frequency of 5 Hertz, which is more than sufficient. And then I set a threshold on the output of the low-pass filter, looking at it after applying the square of the rotational rate. I set a threshold of 0.05. So I guess that'd be radians per second quantity squared. And there's certainly better algorithms for doing zero velocity detection, but this works pretty well, as you'll see. So this shows the smoothed, squared output of the gyroscope, and I've zoomed in on the vertical axis a lot. So this axis goes from 0 to very small values, and the actual signal is way down here until I grabbed hold of that thing and started moving it, and then it jumped up immediately, and this threshold was more than ample to detect when it started moving. There was a period here where I apparently stopped moving briefly, but because I'm applying a low-pass filter, it didn't last long enough to drop below the threshold. So at this point is when it said, okay, you're moving again. So it's a simple algorithm to distinguish the period of movement, which is shown in green, from the period of no movement, which is the rest of the recording. So again, from roughly 0 to 3 seconds, and then from about 8.5 seconds to the end of the recording are the periods where it was still. When I first started working with inertial sensors, I did kind of the obvious thing and set my measurements equal to the things that I was recording. It's called a measurement vector, and surely that's where you stuff all your measurements. It turns out that wasn't the right thing to do. We've talked a little bit about that earlier in this class, but that's what I started doing. And then I figured, okay, and, if I'm trying to model the acceleration, I can use a random walk, and I can do the same thing for the rotational rate. But none of that works because those dynamics are not real at all. This is incorporating prior knowledge that's actually false, because the true dynamics were that sometimes it's still and sometimes it's moving very rapidly. And neither of those are accurately modeled by a random walk. So those dynamics are not real, and when you incorporate that kind of prior knowledge, it just screws everything up. When it's moving, it biases things towards moving more slowly than they really are moving, and when it's not moving, it lets things move more rapidly than they actually are. So it was incorporating exactly the wrong prior knowledge, and it was worse than just doing kind of the naive approach of integrating things. So the movement can be fast, and that's just not a good way to do it. So I thought more about this and did some more reading to see how other people modeled these things, and came up with a better model where I started thinking about the models of the sensors and what the accelerometer was producing. And the accelerometer is basically, because it's in the sensor frame, is a rotation based on what the angle of the device is, what its heading angle is, if you will. It's a rotation of the true acceleration, but I'm also going to measure bias, and there's also noise on the sensor because it's not perfect. So there's a white noise component, there's bias, and then there's a rotation of what the true translational acceleration is in the earth frame. And then the gyroscopes are the true rotational rate plus bias. I guess it's just one channel, so I should say gyroscope, just a z-axis gyroscope. So the true rotational rate plus bias plus white noise, because that's a better model of what that sensor actually does. It's not perfect, it has bias. And this is just a matrix that does a rotation from the earth frame to the sensor frame. I say from sensor frame to earth frame, but I think I got that backwards, because if you're thinking of this as the, oh no, this is the inverse, so that what I said there was right.
Are those vectors?
The A's are vectors, as I've defined here, and omega in this case is a scalar.
And in the theta dot and the bias?
Theta is a scalar. Theta dot's a scalar, this bias is a scalar, that bias is a vector, this noise is a vector. This is two-dimensional, this is one-dimensional.
Okay.
So here's what I ended up with for the process model design. The state vector consists of the angle, the velocities, and the biases. And the angle is equal to what the angle was plus the sampling interval times whatever the gyro is giving me after I subtract off the bias and arguably subtract off the noise. But this is the statistical model for how the angle changes with time. The model, or I should say process model. The process model, and I broke it out as a vector here. This is kind of treating all the variables in vector form, but when you break it out so you can see the different elements, the velocity at time n plus 1 is equal to what it was, plus the sampling interval times a rotation of the accelerometers after subtracting off the biases, because the biases exist in the sensor frame, and arguably subtracting off the noise. After all that, I do a rotation into the earth frame, multiply by the sampling interval, and add it to the previous velocity to get the velocity at time n plus 1. So it's an integration after rotating the acceleration into the right frame. And then for the biases, the knowledge I have of the biases is they change slowly. Whenever you've got that knowledge, a random walk model is commonly used. Especially if you don't have prior knowledge about it being 0 on average, for example, which I didn't know. For a particular sensor, the biases are usually going to be non-zero, so this is a pretty good model. And I can control how rapidly those biases evolve by controlling the process noise on those terms.
So in this case, the accelerometer and the gyroscope are exogenous inputs into your process model? Because you talked about the A's and the theta as being...
Yeah, that's right. That's right. Yeah, I usually call them external inputs, but that's right. I'm feeding them as external inputs into the process model. So that's the process model that I ended up with. Do you understand the thinking that went into the design of that process model? I mean, again, the lazy way would just be to say, oh, the velocity is just do a random walk, or something like that for the acceleration. But in this case, feeding them in as external inputs allows this model, allows things to change very rapidly, and yet it's still incorporating the knowledge provided by the accelerometers and the gyroscope, as well as some of the prior knowledge about how those measurements are not accurate. That knowledge about the bias changing slowly is captured by that random walk component. So this ends up being a 6-dimensional state vector. You've got 1, 2, 3, and then the other 3 for the 3 biases. Yeah? So this is a repeat. It's compact. These are just some of the benefits that I've already said. So I'll go on to the measurement model. Here's some more cleverness, arguably, and others have published this. I'm not claiming that I came up with this. But when the sensor is still, there are things that you know. I mean, when we first look at this, you're like, well, your gyroscope, the only thing that you're measuring is going into your process model. Like, what are you going to do with the measurement model? There's nothing to measure, nothing left. But there is, if you do what are called the pseudo measurements, or I forget what the book called them. The book had a name for these as well. But it's common to incorporate prior knowledge in your measurement model also, sometimes by having, I think the book called them fake measurements. So one of the things I know is when that thing's not moving, I know the velocity is zero. Right? Zero velocity is what it's called, a zero velocity update. So, and part of my state vector is the velocity of how quickly this thing's moving. So I can say, well, if my detection algorithm has detected that I'm in a time of zero velocity, then set that to 0. And I also know that if I'm in a zero velocity period, then the acceleration is 0. The true acceleration is 0, which means when I look at my accelerometers, the only information left on the accelerometers is bias plus noise. And bias is part of the state. So suddenly during a zero velocity period, I can not only, I have a lot of information. I know that the velocity is 0, which is part of the state, but I also suddenly get a way of estimating the bias. I've got visibility, direct visibility into what the bias is during that period. And the same thing applies to the gyroscopes as well. So this is unusual because only during a zero velocity period, suddenly I'm using the accelerometers and gyroscopes as part of the measurement vector, as well as a vector of 2 zeros to represent the fact that I know there's zero velocity at that time.
Are you still running the same process model during zero velocity periods, or you change your process model too?
That's an excellent question. I don't remember what I did. It's better if you change your process model. But I don't remember what I did in this particular example, but that's a great question. Yeah, because you know during these zero velocity periods, if you know your acceleration is 0, then your process model should be different as well. I don't think I did, but I don't know for sure. Great question.
What are you using for your for your thresholding, your zero velocity detection? Are you using the accelerometers?
I just used the gyros in this particular example,
Just
but
the gyro.
you could use both. There's a number of ways. In fact, there are papers written on how to detect periods of zero velocity from inertial measurement units, and I did something very simple in this application. So there's more elegant ways of doing it, but in this case, I just used the gyro. Yeah.
Okay.
So if you do naive estimates, which means you take your sensors at face value and you just integrate them, thank you, and you just integrate them. So if we integrate the x-axis, we integrate the gyro, we get our angle, transform the accelerometers into the earth frame, and integrate the 2 accelerometers. Then you get velocity estimates that look like this, and you get an angle estimate that looks like this. And then once I've got the velocity estimates, I can integrate those and plot that spatially, so you can see what it was, what movement I did spatially as a top-down view as I move this thing around. So if we look at the position, by integrating with this naive estimate, and I gave away what it was signing my name, and that's what the naive estimate is of what my signature looks like. That's not very good. That's not really what my signature looks like at all. But if we use the model, things get much better. So the dark line is the filtered estimate. You can tell the difference because the bias is essentially gone. And you can see the effect of the bias where there's kind of a linear growth in the velocity for both of these signals, and to some extent for the gyro, although the gyro didn't have the same, doesn't end at 0 because this is the angle, not the rate. But in any case, you can see it kind of lays the whole thing down so that the effect of the bias is gone after putting it through the state space model. It's able to estimate what those biases are accurately and account for them so that we don't have that problem. This shows the observations, and this is one of the things I like about this example is the measurement model is time varying. It's only during zero velocity periods where you have measurements. Otherwise, you're just propagating things forward through the process model because you've got no measurements when it's moving. You only have measurements when it's not moving. And so this red signal simply vanishes suddenly when there's movement because we don't know what things are anymore. And so this is showing the these are labeled Y5 through Y3, and that's showing what the accelerometer was during that time. These are the two accelerometers, and this is the gyro. And then the green signal is the bias, so the green is the estimate. And you can see initially it has no idea what the bias is, but within a second it's locked in and it's figured out what the bias is. And then it sort of coasts on that bias until we get over here. And then it picks it up again. And it goes a little bit low and then follows on with the bias. And the same thing with all three elements. And this is just the velocity where there's a 0 red line there where we say the measurement is exactly 0 at that time, and then it picks back up in here. But the measurements are completely gone in this period when it's actually moving. Just able to estimate those biases well. That's the key thing. And this is just showing the residuals. And so I encouraged you to study these. These are basically the innovations. And you can see it takes a while for it to lock on. But as soon as it does lock on, then these are close to 0. And at least visually, those don't look different than white noise. There's a little bit of a transient over at this side, but after a short period of time, again, everything looks very close to 0. I did this with a particle filter. And I like this also. This shows you can see the yellow lines. The yellow lines are the 95% confidence interval in between the yellow lines. The particle mean is shown in green, and you can see all the different trajectories. And you can see them scatter out after the 0 velocity period where you've got that increasing variance with time, where they're all over the place. But the mean is in the right place. And this is showing it for the angle, but it's true for the other states as well. And this is showing the estimated marginal posterior with the techniques that we've talked about in the class, including the 95% confidence interval. And I probably wasn't using enough particles because I don't think that these modes are real. I think that's just estimation error. But the estimate's still pretty good.
Too narrow of a kernel smoothing?
I would say not enough particles, but either one would have fixed that. So this is just the same thing for the velocity in the x direction, and that's the marginal for the velocity in the x, the y, so on. And then I think finally, oh no, not quite. This is the bias. Sorry, I did this as a loop, so there's a lot of sets here that are showing basically the same thing. And then finally the bias z-axis, and it's marginal. And then the effective number of samples, so I was only using 500 particles. For a 6-dimensional state vector, that's not very many. I should have used more. And you can see it was pretty low. There were only roughly 180 of those that were effective when we suddenly hit that period where it was moving. And the number of effective particles stayed constant. So that was another problem, is just when that 0 velocity period ended was at a point where it was about to resample but hadn't quite done it. And so that's the naive signature. And then finally, when you use the particle filter, you get a signature that looks like that. It's much, much better. It's not perfect. I usually circle my name, and so the ending point would be close. But I did this really quickly, and I couldn't see what I was signing, so I don't know for sure that I ended with the IMU in the right place. But huge improvement, right? You can at least kind of make that out if you have an idea of what my signature looks like. Neat. Okay. Scott, could you turn the light back on, please? So I've shown you, we saw from Golriz when she did her homework presentation, she showed some work we'd done with a paper where we were tracking cardiovascular signals. So you got some familiarity. And then I showed you an example with the unscented Kalman filter. But I didn't show that to you with real data. So let me show you what this looks like. With cardiovascular signals, these are measured clinically, often by patient monitors. They'll measure things like the blood pressure, or the electrocardiogram, or the venous pressure, or the pulse oximetry signals that are used to calculate pulse oxygen saturation. So there's a lot of signals, and they turn out to be really interesting. And it turns out you can track them in someone with a healthy heart rate. You can track a lot of stuff with these state space techniques that we've been talking about. So this is an application that I really like, because when you think about it and you think about your prior knowledge, it has nothing to do with spatial dynamics. These algorithms are often tracking like submarines or kayaks or cars going around a racetrack, physical objects that are following Newtonian physics. But you can use them to track other things where you've got prior knowledge about how things change over time also. And with cardiovascular signals, it turns out we've got a lot of prior knowledge that we can bring to bear. So here's an example of a state space model. And again, I did this a long time ago. I would do it differently if I were to do it over again. But here's the sort of instantaneous phase angle of the heart. This kind of represents where it's at in the cardiac cycle. This is the heart rate. And I know that it's going to be bounded. It'll be no larger than some physiologic limit and no lower than some physiologic limit that would represent death. I know that it's going to fluctuate about some kind of mean. So I've got an autoregressive model where it's centered about some non-zero mean. And then, as you saw in the example of the UKF, I've got coefficients for basically the Fourier series coefficients in the trigonometric form for tracking the morphology of the signal. And I used a particle filter in this case rather than the unscented Kalman filter to do the tracking. So this is the process model. This is a measurement model. The dimension is 1, 2, and there's 2 harmonics. So there's 2 here and 2 here. So there's 1, 2, 3, 4, 5, 6. It's another 6-dimensional state vector in this example. And here's everything that I kind of know about this. I was doing a lot of work with children for quite a while, and so the mean frequency is quite a bit higher than the resting heart rate in an adult. That'd be a lot closer to 1 hertz. They said the smallest frequency is 1.5 hertz. The maximum is 3 hertz, which is accurate from knowing children. Knowing about how the heart rate changes, it was reasonable to set the alpha at 0.99. I'm only tracking 2 harmonics because I'm using this in a blood pressure signal that's quite smooth, unlike an electrocardiogram where there are many harmonics. It's very impulsive, so you need a lot more harmonics in a signal like that, but 2 is adequate for this. That was also based on the spectrogram. The initial state doesn't matter so much, but I set the sigma to that for some reason. And the frequency noise is something that I think I just dialed in based on the residuals, based on the innovations. And the measurement noise is something that you know from the instrumentation you're working with. We have a good idea of how accurately we can measure blood pressure, for example. And I'm sorry, I don't remember exactly why I set these as the initial values. I guess I had an idea that the initial blood pressure was around 30 millimeters of mercury, and so I chose that, but I didn't allow any of the pulsatile components to have any amplitude at all. I just let the filter figure out what those were. And it's a really low sample rate. Normally you'd run this at a higher sample rate than that. I guess I was in a rush when I did this, so I didn't use very many particles, and I also always like to push the limits. And I set the resampling threshold at 25% of the particles because I didn't want to resample too frequently to save computation, but I also wanted to have at least 25% of the particles so that the estimates would be reasonable at all times. This is synthetic data, and the true observations are shown in red with synthetic data, and the estimated, or I should say predicted observations are shown in green. So you can see it takes it a minute to lock in, but after a while it looks like more or less visually from this level the green signal's on top of the red, and it's tracking reasonably well. This shows the frequency, and you can see the estimate lags a little bit, which is what you would expect for these state space methods, or causal estimates, so it takes a while for it to detect changes. And initially it has no idea, but it locks in pretty dang fast and does really well on the synthetic data. These are the residuals. I'm finally showing you the residuals, and that looks pretty dang white. It looks pretty unpredictable. I didn't calculate the autocorrelation or the power spectral density, but at least just based on a visual inspection of the innovations, there's nothing there. And when we look at the frequency, which you could only look at in synthetic data, its average is about mean, so it's an unbiased estimate. And you can see there's kind of some slow fluctuations. The tracker can only do so well. But the innovations are white, as you would expect. Filters, hit it too quickly. The sample size, effective sample size. And this is a spectrogram. And again, you see the estimated frequency in green, the true shown in red. And you can see the second harmonic showing up in the synthetic data. You can see the mean fluctuating a little bit by the lower component here. It accounts for sort of a shifting mean in the signal, the trend in the signal. And this is what the innovations look like when you look at a spectrogram. And you look at it and it's completely white, which is awesome. It means you're tracking really well. So the particle filter, even with only 500 particles, is tracking extremely well in this for the innovations. And then these are the state trajectories. This is the frequency, the marginal. I'm sorry, this is a loop. I'm going to go through this quickly. This is the trend. This is the fundamental amplitude for the first component, marginal, second component, marginal. I guess I was looking at the amplitude. Okay, and then finally, real data. This is from a kid who had sepsis at OHSU, and the sample rate was 125 hertz. You'll see in a minute in the signal there was an acute drop in the blood pressure partway through. The poor kid probably was going into shock at that point, which is bad. This is the observed signal shown in red, and this is the point where there's the drop suddenly in the mean pressure. So that means blood's not getting to the organs, and that can be very bad. I can only show you the estimated frequency because I don't have the true frequency. This is real data, so I've only got measurements to work with now. But you'll see there's some really cool insights you can get from the measurements. These are the residuals, and this is the first clue that things are not going maybe quite as they should. Initially, you see the pulsatile components for every pulse because it hasn't locked in yet, hasn't figured out what the frequency is, hasn't estimated the coefficients. But after a while, it does lock in, and it seems like it's tracking pretty well, and yet you see these components, where it looks like something's not quite right. Does anyone have any idea what that is? That it is an iris? You'll probably know.
Additional frequencies? Is it breathing?
Did you say that? Yeah, it's breathing. Yeah, it's the additive component of breathing. When you inhale, you gotta make sure I get this right. When you inhale, you're bringing the air in, you're increasing the pressure. So I believe the blood pressure increases when you inhale, and I think when you exhale, then the pressure decreases. So there are additive fluctuations that's due to the respiratory cycle. If you look at the frequency of this, it's exactly the rate at which this kid was breathing. I think this kid was on a ventilator, which is why these look like they're nearly periodic. He or she was not breathing spontaneously. The weights, we've seen this before. This is just the basic sequential importance sampling particle filter with resampling. Number of effective particles, 125. You can see what happens. Here's the observed spectrogram, and I have to correct what I said. The kid was not on a ventilator, because this is the respiratory component, and you can see there are changes. And this is probably not, sometimes they hyperventilate, but this is unsteady enough that I would wager that is not, that's not a respirator. They were probably quite sick, and so their respiratory rate was nearly constant, but not exactly constant. This is estimated heart rate, and you can see it actually is picking up the fluctuations in the heart rate as well that vary with the respiratory cycle that you can't even make out from the spectrogram. at least with this window size for the spectrogram. And I think, well, I know, even if you made it a shorter window, you wouldn't be able to make that out. So we can actually track with finer resolution. We can track the heart rate frequency with finer resolution than you could ever hope to with a spectrogram, which is pretty neat. You can see the second harmonic. Scott, can you kill the lights one more time? There's one other thing that's really cool here, and I'm sorry, the projector is just not nearly as good as my iPad, but if you look closely, you'll see there are side bands above and below the heart rate of the second harmonic, and they're there for the fundamental also. And that's caused by a combination of an amplitude modulation of the heart rate and maybe a frequency modulation of the heart rate also, both with the respiratory cycle. It has both effects, and there's mechanical explanations of why that happens. But it's pretty cool that all that's in the signal. The tracker is able to track the heart rate really well. If we look at the innovations, this is even cooler, because this gives you the kind of clue that I was telling you about. Initially, it's not tracking. It takes 8 seconds or so before it locks in and gets the heart rate and gets the coefficients where it's tracking accurately. But you can see this fundamental harmonic just completely disappears. It locks in when you're looking at the residuals. So there's nothing left at that frequency, as there shouldn't be. Similarly, the second harmonic is not far behind, where it locks in pretty quickly. There's sort of a ghost of an image, but it's very faint, and it's completely gone by the time you get out here after this acute event that occurred halfway through the recording. So very, very neat. And what pops out when you look at this, at least to my eyes, is that additive respiratory component that we didn't model. Now you can see very clearly, oh, there's an additive respiratory component. We should probably model that, as well as the main component that was so dominant and clear before. You can also see hints of the sideband on the fundamental coming out as well. So this is a really good example of where studying your innovations can give you really good clues about how well you're tracking and whether there are things going on in your signal that you didn't model that maybe you ought to model, maybe you ought to include. Does that make sense? This is a great example of the use of innovations for model design and tuning and diagnostics. Scott, you can turn the light back on. And then, I'm sorry, these other plots are just not very interesting, but this is just showing in the time domain the estimated frequency in the confidence interval, the marginal. Even though I'm using a particle filter, it's clearly unimodal. Should have used the UKF, and once I saw this, using the UKF would be very reasonable. Likewise with the trend and the harmonic amplitude for the fundamental, harmonic amplitude for the second harmonic. And by the way, this is an example of where I'm taking the particles and calculating a nonlinear function of the particles, right? Because this is the square root of the sum of squares of the coefficient for the cosine and for the sine. So this is a nonlinear function. And I didn't just simply take a mean of the state and push it through that nonlinearity. I did it for every one of the particles and then took the weighted average. That's how you should do it. So this is a good example where what I'm interested in is the amplitude, which is different than the state. And I made the states, I designed it the way I did on purpose because it improved the tracking performance to have it be linear in the coefficients rather than do amplitude phase where it's highly nonlinear in the phase. So there were good reasons to do it that way, but then I wanted to see what the performance was of the amplitude, and that's a nonlinear function of the state. So that was done appropriately here. And that's it, more or less. Use the innovations. They are your friends in using this with real data. They should be white. If they're not white, study them, and they should give you clues as to what's going wrong, whether it's a tuning problem or a modeling problem or whatnot. Design your model really carefully. Work with and learn from real data, with the innovations. And I don't think I need to dwell any more on that point about how to handle the nonlinearities. So that's it. Any questions? All right. Well, you guys look exhausted. Good luck on the quiz. I'll see you on Thursday, and I will take any questions you have just prior to the quiz. So as you're studying, if things come up, bring those to class on Thursday, and I'll be happy to answer them.
One question for innovations here. So I don't remember, like in the particle filter, what do we define as innovation?
So I didn't. When I was introducing it, I didn't do it. But you've got all your particles, all your xi.
Yeah.
And you can put those through your measurement model,
right.
All of them.
Which we need to do to compute the likelihood. So.
Yeah, that's right. And you can take the weighted combination, and this now becomes your y hat of, well, n given n minus 1 if these are your predicted particles.
Mm-hmm.
So you can do that.
And this is not going to be the same as if you just took the mean, pass the mean through the...
Yeah, correct. In general, of course, this is not the same as taking the particle mean and then pushing it through your measurement model. Yeah, that's right. All right, good enough. I'll see you guys on Thursday.